Hello? Okay, thanks. Today I'll be talking about Refinator, which is correct, precise, automated C to safe Rust interface translation that enables modular C to safe Rust whole program translation. So I'll start by motivating the problem and giving some background, and then I'll describe the specific interface translation problem that Refinator aims to solve. Then I'll describe how Refinator works to solve this problem, and then I'll show our evaluation results. So why do we care about C to safe Rust translation? Well, the C programming language is famously not memory safe. Memory safety bugs are encountered frequently, and they have an enormous real-world cost, as the last talk pointed out. So there is growing interest in transitioning away from non-memory safe languages like C and C++, specifically transitioning to safe Rust, which is memory safe and performant, and therefore suitable for similar use cases as C, at least for user programs. So one thing we would like to do is automatically translate C to safe Rust in order to remove memory safety bugs. Now, translating C to safe Rust turns out to be hard, and the central difficulty is Rust's strict ownership and borrowing rules, which requires precise whole program reasoning to satisfy. And in the wild, there have been two general categories of approaches. There have been mechanical approaches like C to Rust, which has been mentioned before. And, well, that produces horribly unsafe code, so that's not satisfactory. There's also LLM-based approaches, but if you use an LLM, you also get all of the pitfalls of using an LLM. Namely, you need to verify that the output is actually good. Now, to address the difficulty of satisfying Rust's ownership and borrowing rules, we envision the following translation method, which is also the envisioned use case of Refinator. First, take as input a C program, and then determine a correct and precise safe Rust interface. For our purposes, an interface consists of struct definitions, global variables, and function signatures. And to determine a correct and precise Rust interface requires whole program reasoning in order to satisfy the ownership and borrowing rules. Then, once we have figured out a correct and precise safe Rust interface, we can translate all of the function bodies one by one modularly. Refinator is this first step, this whole program reasoning interface translation step. So what exactly is the translation problem that Refinator solves? Well, to understand that, we'll look at some of the challenges of translating a C program into Rust. So as an example, let's consider this linked list program, something famously difficult to implement in Rust. This consists of two top-level declarations, one struct, which is a linked list node, and one function, push, which takes in an integer and a pointer to node, and pushes into the beginning of the linked list after a dummy node. What we want is, for those top-level declarations, the struct definition and function signature, we want to find a corresponding declaration in Rust. Another way of thinking about this is to find Rust types to replace all of the C types. Now, the challenge is that the Rust interface must be correct and precise. But choosing a correct and precise Rust interface is tough, because a single C type can plausibly map to many Rust types. The most egregious example is the pointer. In C, there's one pointer type, but in Rust, there are tons of different pointer types that behave differently in the context of ownership and borrowing, which leads into our definition of correctness. So we say that a Rust interface is correct if, given that Rust interface, there exists a safe Rust implementation that preserves the copying and aliasing semantics present in the original C program. Now, even though we only care about translating interfaces, the correct interface depends on what the possible bodies of the possible translated bodies are. So Refinator will translate an interface by reasoning about these possible translated bodies without actually doing the translation of the bodies. To understand correctness in the context of this example, I'll point out one way that the correct interface, particularly the interface for node, depends on the body of push. So these are the C semantics that we want to preserve. In the body of push, the C code allocates a node on the heap, gets a pointer to it called n, and then copies n into list arrow next. In order to replicate this behavior in Rust, we have to contend with its ownership and borrowing rules. So a crash course on ownership. In Rust, all objects have an owner, and objects are dropped when its owner goes out of scope. And here, when n is initialized, it owns the node that it points to, and on this line, list.next equals sum of n, ownership is transferred from n to list.next. If you try to write a Rust implementation that avoids doing an ownership transfer, it's not going to work. It's not going to pass borrow checking. So this ownership transfer is necessary. And the necessity of this ownership transfer implies that the type of the next field of the node struct must be an owning pointer. In terms of potential Rust types, this rules out certain Rust types like references because you can't transfer ownership to a reference. But other types, such as this complicated option RC ref cell node, are OK. Now, in this example, it's possible to pick a single Rust type for the next field of node based on correctness alone, but that's not true in general. For our next example, we'll consider the list parameter of this push function. To choose a single Rust type for this, we also need to consider precision. So obviously, since in C we have a pointer to node as the type of this list, when we translate to Rust, we also must pick some kind of pointer to node. Correctness rules out some of these types, namely this immutable reference to node, because the body of push will mutate the list argument. But there are a bunch of other pointer types that are OK. What we would like to do is we would like to choose the simplest, least costly correct type according to some cost function. Refnator's cost function says that these two types, which involve dynamic borrowing, are correct but not precise. But this native mutable Rust reference is correct and precise. So that's our translation problem. Now let's talk about how Refnator solves that translation problem. First, let's look at the general architecture of Refnator. Refnator takes as input a C program and then converts it to an intermediate representation. This is a 3-address code-based representation, which is useful for generating constraints out of. And then based on this intermediate representation, Refnator generates a bunch of SMT constraints and then plugs these SMT constraints into an off-the-shelf SMT solver. In our case, it's Z3. And then the solver will spit out a assignment of Rust types to C types, and that gives us our Rust interface. Next, we'll talk about some of the technical insights that make this possible, and we'll look at what some of these SMT constraints generated by Refnator are. So the first technical insight is that in Refnator's IR, C types are encoded as type fragments. So occurrences of C types are enumerated, and these occurrences come from struct fields, function returns, variables, and R-value expressions. And then these C types are broken up into fragments. If you look at the very bottom R-value expression, n, this has the C type pointer to node, and it's split into 2 type fragments, the pointer part and the node part. Then Refnator finds an appropriate Rust type, or part of a Rust type, for each of these type fragments. The advantage of using type fragments instead of reasoning about entire types at once in the constraints is that this allows the constraints to be simpler. This improves the performance of the SMT solver, and this also allows for the level of indirection of whatever Rust types are inferred to be adjusted as necessary. Another technical insight is that the SMT constraints generated by Refinator consider pointer transformations. So when choosing Rust types, pointer types are allowed to mismatch in certain contexts as long as the transformation is allowed to rectify it. This allows more correct types to be used than would otherwise be possible. So this picture shows all of the transformations considered. There's a lot of them. And the details are in the paper. So with these insights in mind, Refinator generates the following 4 categories of constraints. 3 of these categories deal with correctness. These are consistency, semantic preservation, and borrow checking. More about these later. And there's one final category that ensures that precise types are chosen, and this is encoded using optimality objectives fed into the SMT solver. First, let's look at what a consistency constraint might be. So the consistency constraints ensure that the Rust types chosen are consistent with the C types in the input program, and that the Rust types chosen are consistent with themselves. So like you can't have infinite structs or stuff like that. An example of a consistency constraint is that all of the chosen Rust types must match the C types in the input. In this example, we have the signature of the push function, which takes in a pointer to a node and a 32-bit integer. So obviously, our pointer to node in C maps to some kind of pointer to node in Rust, and our 32-bit integer in C maps to some kind of 32-bit integer in Rust. Our next category of constraint is called semantic preservation. What that really means is that the copying and aliasing behavior in the input C program must be preserved in a Rust translation. So as an example of a semantic preservation constraint, here, if the Rust type of the variable n isn't a copyable pointer, then the bold purple R value expression must not transfer ownership of n. And this matters because in Rust, only certain Rust types can be copied, and for pointers in particular, you can't just copy any old pointer. Like in C, you can only do arbitrary copies with certain types. And this constraint falls out from these facts. First, n is used in this call to replace first, and then it is used again at the end of main. Second, if n cannot be copied, then the ownership of n may be transferred, depending on what you choose as the type of this R value expression on the Rust side. Third, if ownership of n is transferred at that purple R value expression, then we can't use n at the end of main. So we end up with this constraint. And since in this particular implementation, n is a box of node, which is not a copyable pointer type, the type of the Rust types of this R value expression are constrained. So we cannot use something like a box of node because that would force an ownership transfer and violate this constraint. But we can use something like a reference to node or a mutable reference to node. Our third category of correctness constraint is the borrow checking constraints. These effectively mimic the Rust borrow checker and ensure that the translation can borrow check. So background on Rust borrowing rules. First, an object cannot be mutably borrowed by more than one mutable reference at a time. And second, an object cannot be moved while it is borrowed. A constraint that's generated by a Refinator that falls out from these borrowing rules is that if list here is borrowed at this start point in the program, then the type of the purple R value expression inside this call is some kind of shared reference. In this particular Rust implementation, list is borrowed by sublist in the boxed region. Therefore, list is already borrowed at the start point, and this use of list must translate to some shared borrow. What this means is that the types of this R value expression on the Rust side are restricted. So something like node, a bare node, is not allowed because that would force an ownership transfer, and a mutable reference to node is not allowed either because that violates exclusivity of mutable references. But something like a shared reference to node or even a shared reference to ref cell of node is allowed. And that concludes our discussion of the constraints. Now, how well does Refnator work? So we evaluated Refnator based on 3 metrics. The first 2, correctness and precision, we've already talked about. And the third one is performance. Yeah. And for the performance metric, what we care about is how long Refnator takes to infer an interface, not its runtime performance. And we evaluated these 3 metrics on 9 benchmarks. One of the benchmarks is the program that we've been looking at in our example, and 8 programs come from CrustBench, which is a C to Rust translation evaluation suite. We evaluated the following 6 constraints for all 3 criteria, correctness, precision, and performance, and we evaluated these additional 3 for performance only. Now, out of all of the interfaces that we evaluated for correctness and precision, they were indeed correct and precise. Now, for performance, we saw something a little interesting. The analysis time, which is the time that it takes to generate constraints, was very low across the board. But the solving time, the time that it takes for the SMT solver to solve the system of constraints, was very large. It dominated. And we also noticed that this increased very quickly. So one example was Arbitrary, which is, this is a lab from CrustBench, and it's about 350 lines of C code, but it took about 20 minutes to solve. OK, so that concludes my talk. In conclusion, Refnator is correct, precise, automated C to Rust interface translation that enables modular C to Rust whole program translation. Thank you.
All right, let's go to the questions. And yeah, I saw that there's too many.
Hi, great talk. So you gave an example of a linked list in the first place. What if that were a doubly linked list? Would your translator, like, how would it handle that?
It would still work. So actually, it would use the same types. It would still use RCs of ref cells for both the forward pointer and the backward pointer. So yeah, it works just fine with a doubly linked list.
So I don't quite get one of your previous examples. Could you just roll over a little bit?
Yeah.
So yeah, here the replace first function on the right-hand side is supposed to mutate the list, right? But you only have an immutable reference here. So is it a successful translation, or what's happening here?
Let's see what's going on. So one way that we can get so it could be a correct translation depending on what the type of list is or how the node struct is defined. So it's possible to use interior mutability here to mutate the list even though it's passed into replace first as an immutable reference.
You just now mentioned that when translating doubly linked list, you also use optional RC. However, for reference counting, if there's a cycle reference, there's going to be a memory leak. Have you ever accounted for this problem?
So we don't specifically account for memory leaks. We don't have any guarantees that the translated interfaces will admit an implementation that's memory leak free.
OK. Then let's thank our speaker again.